Okay, welcome back. I hope you all had a good lunch or a good rest or whatever you did during the 2 hours. Our first speaker today is Joyce Guzik, who is going to follow up, well, not follow up, but expand upon the last talk that was given at this morning's session. So let's welcome Joanne Guzik.
Okay, thank you. Thanks for the opportunity to present to you. And I think I'm going to learn more from all of you than you will from me, perhaps, because I have many puzzles with light curves and Kepler data that I could use some help trying to understand. So I'm going to talk about main sequence variable stars, and I'd like to acknowledge my co-authors, my student from 2 summers, Katie, my colleague from New Mexico State, and my colleague from Los Alamos. So as you've heard from Horace's talk earlier, there are many, many kinds of pulsating stars, and stars of almost every age and evolutionary state show pulsations. And I've always been interested in trying to use the pulsations, especially of multimode pulsators, to infer the internal properties of stars. I started at first working on the sun, and now I've expanded to looking at stars, a little bit more massive than the sun. This is the sun and solar-like stars. I'm mostly going to talk about the Gamma Doradus stars, which are about 1.5 solar masses, and the Delta Scuti stars here, which are about 2 solar masses. I'm mostly focusing on the ones near the main sequence that are not the high amplitude ones. And if you go up further on the main sequence, we have the slowly pulsating V stars and the beta Cepheid stars. Beta Cepheid stars. So the sun pulsates in pressure modes. We haven't been able to find the gravity modes yet, of about 5 minutes. The Gamma Dor stars pulsate in gravity modes, and their periods are about 1 day, which makes it really hard to take, a point every night and get a light curve because of the 1 cycle per day aliases that can come into your data. The Delta Scuti stars are about 2 hours. If you go back to SPB and Beta Cephei, you have G modes and P modes again, a few hours and again about a day periods here. Okay, let's try this. So you've already heard a little bit about the NASA Kepler mission. It was launched in 2009, and it focused on this area in the Cygnus Lyra region, looking for planet transits over stars. But as a secondary mission, it can and it did look at many, many stars for years at a time in some cases, in both short cadence, taking one data point every 5 minutes, or 1 minute, 1 minute, I believe. I usually don't use the short cadence data, and the long, because it's very expensive to take a point every minute and send all the data back to the Earth. And the long cadence data was 1 point every 30 minutes, and the precision was very, very high. Now, you don't get every one of these stars back because they can't send all the data back from the spacecraft every month, so you had to propose which stars you wanted to observe, and then several months later you would get the data back. Every 90 days or so they would send the data back to the Earth from the ones that were requested. So I'm going to start now talking about some of the unsolved problems that the Kepler data have revealed or are helping to solve in these main sequence stars. So this is the part about the hybrid Gamma Doradus and Delta Scuti stars. So in Kepler, we found many faint stars that were Gamma Dor and Delta Scuti candidates. And I'm saying candidates because we haven't verified with spectroscopy the exact effective temperature and surface gravity, luminosity, derived all the stellar properties for these stars. So it's not clear where they may be in the main sequence, although we have some idea from the Kepler input catalog and the colors that were available in that catalog. So in this case, I have a light curve for a Gamma Dor star, and there are 2 main periods here, about between 1.5 and 2 cycles per day, that are beating against each other. And this is the light curve, and you see you get this ringing as they interfere constructively and destructively over time. So this was a very good example of a light curve from a gravity mode pulsator Gamma Dor star. And here's a star that is a Gamma Dor Delta Scuti hybrid star. It has many periods around 1 cycle per day. These are the 1 to 5 cycle per day blow-ups. So you can see periods here around 2 cycles per day. And then here's a whole bunch of periods around 20 cycles per day. And these are the delta Scuti modes. So this pulsates both in pressure and gravity modes. They sample different parts of the star. And if you could model the star and figure out what all these modes were, you could tell a lot about the structure of the star. Where are the convection zones, how old it is, how much hydrogen is burned in the core, what the composition is. You could tell all kinds of things if we could disentangle these frequencies and understand what they are. So the Gamma Dor and the Delta Scuti star pulsations are driven by very different mechanisms. The Delta Scuti stars are pulsating because of helium ionization just at the right layer in the star. This is the surface of the star, and here's the center at 10 million degrees. And if I plot the opacity, which is a quantity about that tells you something about how opaque it is, how hard is it for radiation from the center to get out to the surface, you see that that is not just a straight line, but it has bumps where different elements are ionizing. And if they're in just the right place, they can dam up radiation trying to come out, and they can cause a work cycle that makes the outer envelope expand, and then it comes back in again, and then it pushes it again, and it goes back out. So for these Delta Scuti stars, the second helium ionization is just at the right place to bottle up radiation and cause the pulsation driving. Let's see, I've got to back up here. Okay, for the Gamma Dor stars, I know this is a busy plot, so I don't want you to focus on everything, but the Gamma Dor stars are a little bit less massive, and they have a bigger envelope convection zone. So this green-gray area out here is where convection in the outer part of the star is carrying all of the energy out of the star, and radiation is carrying it here. So the radiation's coming out, and when it gets to the bottom of the convection zone, it would really rather have convection carry out the energy. But because convection takes a while to get going, and the convective time scale down here is quite long, longer than the pulsation period, this radiation gets periodically blocked, and that's why it's called the convective blocking mechanism for Gamma Dor stars driving the gravity modes. So if this layer is at just the right place, if it's too deep, the radiative damping, which is happening down here, this is the work, so the integral under this curve has to be above 0. If it's too deep, you get too much of this radiative damping. If it's too shallow, then convection is going much more vigorously and it has a much faster time scale, and it can take the energy away, so it's not blocked up. But if it's just at the right temperature, around 300,000 degrees, that's where these gravity modes can be driven. So before Kepler, we had a very clean picture of the Gamma Dor stars and the Delta Scuti stars above them, and we thought we understood these driving mechanisms quite well. So before Kepler, most of the Delta Scuti stars were here in the Delta Scuti instability region. These are just lines drawn from all of the ground-based discoveries of Gamma Dor stars, or Delta Scuti stars rather, and the blue stars here are the Gamma Dor stars. And we had some hybrid Gamma Dor stars and Delta Scuti stars, just a handful of them before Kepler. Here's 3 of them, these black dots here, and they're very close to this region here of overlap between the Gamma Dor instability strip and the Delta Scuti instability strip. So it kind of makes sense that you could have hybrid stars that can manage to pulsate in both types of pulsations, and Delta Scutis and Gamma Dors. So everything looked pretty good. But after Kepler was launched, this is one of the first papers of looking at some of the brighter Gamma Dor and Kepler Gamma Dor Delta Scuti candidates. The red stars, again, are the Delta Scutis, and you find them all over the place, including there's some down here in the Gamma Dor region, these red squares. And you find Gamma Dor stars all the way up here toward the blue in the Delta Scuti region, and we find many, many hybrid stars that pulsate in both types of modes, scattered all over the diagram. Now, some of this scatter may be because these stars don't have accurately measured effective temperatures or surface gravities. So hopefully some of that might clean this situation up. Some of these G modes might be something else. They might be a rotational period instead. So there's a lot of work to do to try to understand why there are so many hybrids and why the stars don't seem to be in the right place in the HR diagram. And this is a little bit a set of some fainter stars that I looked at, requested as part of the Kepler Guest Observer Program. And those two first stars I showed you, the Gamma Dor and the Delta Scuti star, this one, I believe, is the Delta Scuti. Now, that's the Gamma Dor star, that's right. The first Gamma Dor star I showed you, but it's over here, way far in the blue in the Delta Scuti region. It should be over here, but it's over there. And the other star that was a hybrid is over here, but it should be over here. So if I did a model of this star, I wouldn't predict that gravity modes would be pulsating in either one of these. But there they are with gravity modes pulsating. Okay, so another problem is that we can find stars that aren't showing any pulsations at all, but they're in the pulsation instability region. So this is a summary of the Kepler Guest Observer Program stars that I looked at. I had 633 faint stars in quarters 6 to 13 of the Kepler mission, and then later in quarters 14 to 17, I asked for 2137 more stars, and I tried to pick stars in or near the instability region and on the main sequence of particular effective temperatures and log surface gravity. And I have long cadence data, and I was looking for stars that showed no variability down to 20 parts per million, which is pretty low. That's about the most accurate I could get on these faint stars. And we also tried applying an increase in the temperature, which was suggested by comparing the Sloan Digital Sky Survey photometry with the Kepler input catalog for the stars of this temperature. It looked like there was sort of a 300 Kelvin offset. So I applied that as well to move the stars around, and that does move them, some of them in to the instability region. So in that first set, I found a lot of stars that were constant, that are outside the instability region. But I have to say, I also found Gamma Dor stars that were way down here too, that should have been over here. But in general, I found 6 stars that were in instability regions that were completely constant, no pulsations, down to 20 part per million level, that should have been pulsating. And looking at the next sample of 2138, I guess, stars, I found 46% of those were also not pulsating, and I have 34 stars here in the pulsation instability regions. If I decided not to apply that offset that Pinsino et al. Recommended, a lot of the stars move further to the red, and I only have 17 stars still in the instability region. However, some of these are pretty hot, 8,000 degrees. They really should be Delta Scuti stars, but we don't see any pulsations in them at all. So these are some light curves just to show you the parts per million level. This is the light curve. This is the amplitude spectrum total. This is blown up looking at the lower frequencies and the higher frequencies. 10 cycles per day, I don't see anything above 10 cycles, or not 10 cycles per day, 10 parts per million. I don't see anything above 10 parts per million in these. And here's another one, nothing above 10 parts per million. It should be a Delta Scuti star, 7,800 degrees. And here's another one, 7,200. It should be a hybrid Gamma Dor Delta Scuti star. There is nothing like to 5 or 10 parts per million in this light curve. And you see here's the 1 quarter, another quarter, and part of another quarter here. So that's a mystery I could use some help with on understanding why are there these constant stars. And I'm going to go on and talk about another topic, and we've heard a little bit about this before too, amplitude variations. Why do we get variations in the amplitude of the different frequencies of the main sequence variables? We don't expect them because for single stars that are unstable, the pulsation properties are determined by the structure of the star, and that changes very slowly over evolutionary time by nucleosynthesis or by cooling. So we wouldn't expect over the a few years of Kepler data to see amplitude variations. And timescales for evolutionary processes are hundreds to thousands of years instead of hours to years over which we have this photometric data. Um, Pulsations should grow relatively quickly to reach a limiting amplitude and then stay constant. Here's just a picture of a B star radial pulsation that I ran in a code that grew, and it grew to some amplitude and then it levels off and stops. But stochastically excited pulsations like those found in the sun or in red giants, they're continuously excited and damped, so you do expect the amplitudes to vary, but not in these intrinsically unstable stars like the Gamma Dor or Delta Scuti stars. You don't expect to see that. But these amplitude variations could be very important for the physics. They may tell us something about energy partition or exchange between modes. They might tell us something about internal dynamics like convection, rotation, magnetic fields that may be exchanging energy with the pulsations, or even changes in the ionization regions deep inside the star. So they're very interesting to study. They may indicate also an interaction with an external environment, like a planet or a binary star that we can't see, or tell us something about accretion from a disk or a nearby star. And they can also help us to validate multidimensional nonlinear pulsation modeling that we're just starting to do now in recent years. So amplitude and frequency variations, despite being unexpected, have actually been observed in nearly every type of pulsating variable, again, including our Delta Scuti and Gamma Dor stars, stars on the main sequence, rapidly oscillating AP stars, even in white dwarf stars. So they're everywhere. We've seen examples of amplitude variations like in the Blazhko effect in Cepheids and Aurora stars and in Mira stars. So I've been trying, and I've just learned a little bit about doing this in the last couple of summers with my student using the V-Star software from the AAVSO, and it has a weighted wavelet Z-transform program that will look for changes in amplitude in individual frequencies or in individual modes in these multi-mode pulsators. I learned about this software from John Percy a couple of years ago and then decided I should have my student try it. And independently, I've had my colleague Jason at New Mexico State write a MATLAB script to do wavelet analysis because he was familiar with this from doing solar-like stars. So with these, you take your long time series and you break it up into little pieces, and you can either just have a moving window, maybe use 50 days of data and just keep moving it along and look at what the frequencies are and look at what the amplitudes are for that 50 days, and then you move it over again and you see if the amplitudes changed in that particular mode in the next time slice you use. And you can make these kind of close together so you can watch the amplitude vary over time if it's going to do so. So I've been trying to apply this to my samples of Delta Scuti Gamma Dorada stars. So first I'd like to show you this one particular star which had a really dramatic change in amplitude of one of its modes. This is the star KI Kepler input catalog 7106205. It has an 11.5 magnitude Kepler magnitude, and this is reported by Bowman and Kurtz in 2014. So they looked at all the modes of this star, which had pretty high amplitudes, 100,000s of parts per million. And this particular mode over here at 13.4 cycles per day, while they were looking at it over hundreds of days, several years of data here, this mode dropped in amplitude all the way from whatever 5,000 ppm down to practically nothing. And all the other modes in the star stayed constant. Now this analysis was done by us with Jason's software, so I could verify that the software was working. So you can see that we could reproduce this, and we have no idea why this is happening. Why did that one Delta Scuti-like mode just drop where all the other ones stayed at the same amplitude? So this is one of the first stars that we looked at that was pretty interesting. This is a fainter star, a 14 magnitude Kepler star, KIC 2167444, and it showed in its highest amplitude mode here, which is, I don't know, 3000 ppm, it showed oscillations of about 28, 29, 30 days in its amplitude. If you just broke up the light curve, which is broken up here, this is the light curve, but you see we have long sections with no data, and here we have data, and here we have data. But where we have data, it's oscillating. And I looked at the other modes in this star, and a couple of them are also oscillating with that period. Let's see if I can get this to work. The second highest amplitude mode, which was very close to this one actually, has some oscillations that seem to kind of go away over here in this longer time series. And then there's some lower amplitude modes that do, but then others are pretty flat. And using the V-STAR software, we also found these variations. We were just looking at it 1 quarter at a time. So this is the highest amplitude mode. The second highest amplitude one seems to be following it, maybe a little bit of an offset in time. And here's another third highest amplitude mode. And if I look at all 3 quarters that we have data for, 4, 12, and 13, I've hoped that we could get the color code the same on all these. They're not quite. The highest amplitude mode is going up and down in all 3, although it's got a different amplitude in kind of each one a little bit. And the second highest one is following it, a little bit of an offset. And the third highest is the gray, but over here in quarter 13 it gets really incoherent, and this other 3.4 cycle per day mode starts to be more prominent. So from quarter to quarter, which mode is dominant, or the order of dominance is changing, and there are these oscillations. Now I think what may be going on in this star is that these 2 highest amplitude modes are interacting, because their period difference or frequency difference is just about right to account for that oscillation. So I need to verify that and understand what's going on, but there are other examples in the Kepler data that are showing interesting differences. Why some of the modes are varying and others aren't is still quite a mystery. So I'm going to show you a little bit. How much time do I have left? Can you give me some idea? I just want to make sure I'm not going to go way over. Okay, about 7 minutes. Okay, thank you. There are a lot of expected and unexpected patterns in the frequency spectrum of these stars. Solar-like oscillations are expected to show very regular frequency spacings. Delta Scuti stars aren't, because they're pulsating in low-order modes and have a mixed P and G mode character. And Gamma Dwarf stars are expected to have regular period spacings on the G modes. But we have a hard time seeing those patterns and identifying modes for these stars, because not all the modes that are expected from stellar models are observed. As you saw, we saw a couple of really high amplitude modes for that first Gamma Dwarf star. And overlapping multiplets from rotational splitting, these stars are faster rotating than the Sun, can also really complicate the mode identification. So here's a shell diagram where you take the frequency modulo a particular characteristic spacing and wrap it around, and then look for a ridge or a pattern that all the modes show. And here you see there's a characteristic spacing for the Sun of 134.6 microhertz, and you can just line up all the L of 2, L of 0, the radial modes, L of 3, and L of 1 on a ridge, and then you can identify all these modes exactly with what mode they are. So for the Sun, mode identification is pretty easy. But for Delta Scuti stars, as they evolve, you start to get a G mode character for all of the P modes. This is with time. Here you've got some pattern of modes of different frequencies, and as it evolves and you get a composition gradient in the core and a cavity forms where G-type nodes can exist, you start adding more and more modes close together, and these things that are kind of constant move over These are called avoided crossings, where these modes they don't actually cross frequency, but they shift and change. So finding a pattern in this is really hard when you don't know the age of the star, you don't know the mass of the star. It's really difficult. And the other problem is rotational splitting. The Coriolis force and the centrifugal force takes every degree L mode and breaks it up into 2L plus 1 multiplets. So here would be for no rotation, and then when you add the Coriolis force, you maybe for L of 2 get 5 separate modes with this XX-Pix delta Scuti model. Then if you add the centrifugal term, you break the even splitting. So now you have modes of different radial order. All their frequencies are overlapping with the previous one, and there's no nice pattern anymore. Also, there's a problem of combination frequencies. In this Kepler star, 9700322, there were 80 frequencies found, but after Mike Breger looked for all the combination frequencies, he found that there were really only 2 dominant frequencies, and then a quintuplet that you have to pre-whiten these out to even see, and everything was a combination of those 5 frequencies plus the rotation frequency. So all of these 80 modes down here, you could boil it down to 6 frequencies and understand that, but even those frequencies, you don't know where they came from because you're expecting more intrinsic frequencies. These two don't agree in period ratio with what you expect from a delta Scuti star, so it's really hard to figure out what's going on. Nevertheless, people have been forging ahead to try to find patterns, and this is Margit Papireau's paper very recently, where she was trying to look for spacings in Coro stars that had hundreds of frequencies, and she found many characteristic spacings, and she was able to put them on a shell diagram ridges. But what do these mean? We tried using the delta Scuti star FG-Ver to figure out what they might mean, and even though these things, don't line up on, I'm going the wrong direction, don't line up on L of 0, 1, 2, 3 ridges, you can still find ridges and a characteristic spacing, and that seems to correspond pretty well with theoretical models, which can give you a mean frequency spacing and a mean density. Here's a mean frequency spacing versus mean density for some delta Scuti stars from models, and here's Margit's stars all put on a line, the same line that goes through this theoretical model. So maybe these characteristic spacings can tell us something about mean density, even though we can't identify the mode. So we found, there was one paper I thought was interesting here, a slowly rotating gamma Dor delta Scuti hybrid in a binary system. This is a really new paper by Van Rieth et al. They were able to find evenly spaced gravity modes, very low amplitude, just like you would expect in the theory. So I was really impressed with that. I don't know if I'm going to run out of time here, but I want to tell you about one more topic, and that's the solar abundance problem and how stars can tell us something about, maybe help us figure out what's going wrong with the sun. As you may or may not know, in the year 2004, they reanalyzed the spectrum of the sun, and the amount of heavy elements, especially carbon, nitrogen, and oxygen, went down. So instead of 1.8%, 1.8% heavy elements in the sun, we're down to more like 1.2 or 1.4%. And our solar, mostly oxygen, carbon, and nitrogen went down. And when we used to use helioseismology to figure out the sound speed in the sun, this is the difference between the inferred sound speed and the model sound speed. When we used to do that with the old abundances that were the 1.8%, we got pretty good agreement to within 0.4%. Now when we use these new abundances, we're off by 1.4, 1.5, 1.6%. And the error in this inference is only about the width of a line in these difference calculations. So we have a problem modeling the sun with these new abundances. So we've tried tried to, at Los Alamos, come up with a new generation of opacities, and these opacities are a little bit bigger, and those help with the solar abundance problem. So now, rather than being 1.4% off or 1.2% off, but that's still not acceptable. And it turns out other stars, like the SPB and Beta Cephei stars, they pulsate because of heavy elements in their atmosphere. In the case of these stars, it's iron group elements, iron and nickel. And they also have a problem. In the Kepler data and even in ground-based data, they show, going the wrong way again, back it up. They show frequencies. These are the growth rates, or whether these modes are predicted. They show frequencies that, well, here the models predict some things that aren't there, but they don't predict some frequencies that are there. And the same is true for 12 lac. There's a G mode predicted that is almost impossible to get to predict to be excited. So the new opacities help make the instability strips wider, but not wide enough. And this is a picture showing just increasing the element abundance. And all the way up, we aren't able to get that 1G mode to, even with the new opacities or even increasing the abundances, get it to pulsate. However, if you take the opacities, multiply them by a factor of 2, you can actually get 12 lac and that other star, New Eridani, to be in the instability strip. But no one believes a factor of 2 increase in iron opacities. That's quite a lot. So I'm going to stop right here. I have a lot of K2 data that I'm trying to interpret. Here's an example of an eclipsing binary. Here's an example of a delta Scuti Gamador hybrid. And I would love some help with trying to decipher these light curves from K2 because they don't make any sense to me. All right, thank you.
Thank you very much. I think we have time for 2 questions.
Yeah, that's a very fascinating and amazing set of material. One of the last subjects you mentioned about the reduction in metallicity of the sun. Can you just give me a little bit more information about that, the reduction in carbon oxygen? That was fascinating and timely, given we're coming to towards the end of the current cycle and lots of concern about whether there'll be any sunspots next cycle. I just wonder what some of the big views are on this.
Well, the reduction was not due to actual changes in the sun. It was changes in interpreting the solar spectrum. They improved their modeling of the spectral lines in the sun. Okay. And then they reanalyzed this with 3D model atmospheres, better non-LTE effects included. And so even if you used a spectrum from hundreds of years ago, you would have gotten this answer. But they just redid it with better physics, better interpretation. But it is a real problem because you say solar abundance. The question is, what is solar abundance, right? Every star has different abundances, but even stars the same age as the sun may. If we say they're solar, we need to know what we mean by that.
Okay, one more.
Joyce, the question of the constant stars, you've definitely eliminated these are not metallic line stars?
No, we haven't.
And I'm not that familiar with the photometric bands, or not familiar at all with the photometric bands of Kepler, but is there any means of getting an estimate of the metallicity from the photometric bands?
There may be. These are the ones that I showed you that we had looked at were quite faint. They were 14, 15 magnitude. So we would need to find some spectroscopy or something to get a better metallicity. Simon Murphy and colleagues have published papers looking more at the brighter stars that they thought that were supposed to be constant, and they found that either their temperatures were way off and they should be outside the instability region, or they were, as you said, metallic line stars. So it's possible that elements or helium have settled out, and so that the pulsation driving mechanism doesn't work anymore. Right.
Certainly the metallic line stars there's virtually no overlap with the pulsators. They're all slow rotators. So I haven't read anything for a long time, but I thought it'd been pretty well established that the diffusion theory and the idea that the slow rotation was inhibiting pulsation. I've got a couple of references if that's of any use to you.
Right. I think I've seen the theoretical work, but I'm wondering if these stars will fit in with that theory. Because we should look and try to measure these very precisely.